Hello, my name is Tom Reeser. I'm the Director of Fireline Global here in Vancouver, Washington. The purpose of my talk today is to have a very simple, basic overview of how to size a foam pump and what a foam pump really is. Most foam pumps in the world today are a positive displacement pump. And what I mean by that is there's some form of gear, either a spur gear, a helical gear, or a herringbone gear, that creates a void when it rotates this direction and comes out of mesh. In this particular direction of rotation, that would be the pump suction. And as the teeth come out of mesh, that creates a void. And if the inlet of the foam concentrate is here, it would fill the rotor cavity in each rotor tooth as it rotates around the casing. And then that fluid is trapped in here. And conversely, when it's rotating on the discharge cycle, the fluid would be carried, of course, in the cavity here, as I mentioned. And if this would be looking at the discharge port, when the pump rotates this way, as those teeth come into mesh, the void is reduced, and obviously the liquid is displaced. Thus the word positive displacement, because the liquid indeed has nowhere to go. So that's the basics of a positive displacement pump. Again, they can rotate either direction, and this could be suction or this could be discharge. Just another brief overview, there's always a bushing or a bearing of some sort, and in our case, a single lip seal. And the materials are usually bronze, in this case with, in our case, a duplex stainless steel shaft. But they're just about always bronze or stainless because foam is corrosive and they're very often flushed with seawater. So it's important to understand, in closing on the positive displacement principle, that as you can probably imagine, if you're rotating this and a valve is closed or the discharge is restricted, you must use some form of a pressure relief valve to relieve excessive pressure to protect the downstream piping components, valves, fittings, check valves, so on. So this is always mounted in the discharge side of the pump piping to prevent and relieve excessive pressure. At Fireline, we do extensive 3D modeling and printing of our rotors. This is an example of a larger rotor that has been 3D printed, but the stress calculations have been laid into with color into the 3D model. And what we're looking for is any red spots or which indicate problems in the design. So that's part of the process we use here at Fireline to design our pumps. We have recently achieved UL-FM, UL listing of our foam concentrate pumps and FM approval on a global basis. This is the tag that goes with the foam pump skids. And then I wanted to move into just basically how to size a foam pump. So what I did on the board here is kind of come down with some basics here. When you contact Fireline Global, we're going to need some basic data from you, like the foam solution flow rate. You should know that based on the square footage and the density that you wish, either 0.01 GPM per square foot or higher, depending on the hazards. The foam solution discharge pressure at the injection point. The water pressure at the point of injection is very, very important. And of course, then the type of foam concentrate and the percent for injection that you're going to use. Typically in the world today, that is either 1%, 3%, and in some cases 6%, but we don't see that much anymore because of the technology of the foam concentrates. In my example here, I've picked 1,000 GPM of foam solution. So the design engineer the fire protection engineer would come up with that solution flow rate based on the hazard and square footage or square meter that they're trying to cover. And in our example, we're going to use 3% AFFF, which is a very common worldwide common foam concentrate. So it's pretty easy math. You take 1,000 GPM times 3% and you come up with 30 gallons a minute. So you say, oh, that's what my foam pump needs to be. No, that's not true. So that's your minimum flow rate you'd have to design for. What we always recommend is you add at least another 15% for the foam concentrate capacity. In this case, that'd make it about 35 GPM. And the reason we do that is, what if your system flow rate is a little bit higher than your design calculation of 1,000 GPM? Or what if the discharge devices, sprinkler heads, monitors, floor nozzles, whatever they may be, actually flow a little bit more than what you predicted? Or conversely, your pressure, your discharge pressure is a little bit higher than you calculated. Then you're going to flow more through a given orifice. So we always try and add a minimum about 10 to 15% overcapacity of the foam pump. And the other reason we do that is that in a balanced pressure foam system, there is a valve, either called a pressure sustaining valve or a balanced pressure valve, that has to modulate or work to maintain the set pressure that you design for. So if you have no flow going through the valve, obviously it can't control or modulate. So it's got to have a little excess flow to, again, modulate and do its job and maintain a steady foam pressure at the proportioner. The other thing, and speaking of the proportioner, is, in my example, we have 150 psi water pressure. Would you design for that water pressure for your foam pump? No. You'd always want to add 15 to 25 psi or 1 to 2 bar greater pressure than the water pressure to ensure that you've got positive injection of foam concentrate into the water stream. And again, this could be because the water system is a deluge system. It's a little bit easier to calculate, but if it happens to be a zone system or a closed head sprinkler system, the water pressure curve on your centrifugal pump is always looks like this, with this being quantity and this being, of course, head. As you go back and restrict and say your design point is here, as you restrict the flow, you're going to get higher and higher pressure on that pump curve. So we always have a little extra pressure in the design of the foam pump, the capacity that is on the pressure. You may have to have a little bit higher horsepower or kilowatt driver, but given the size of a 30 to 35 GPM foam pump, it's inconsequential. So in this case, we're going to end up with a foam pump that's got 35 gallons a minute of capacity, and we're going to have a foam pump that's going to equal 175 psi discharge pressure. And finally, in this very short example, how are you going to drive it? The primary choices out there today are an electric motor, a diesel engine, usually ULFM diesel engine, a water turbine or water motor, or in some cases hydraulic. That's how you're going to motivate or drive the foam pump. So you've got to give consideration to the electrical service in the site area. Or do you want to use a diesel engine, which is a little bit more costly typically, but it does not rely on grid or incoming electrical power. And of course, water turbine is a very good and low-cost method. However, you've got to have the excess fire water capacity to turn the water turbine. So in our case, we'd select a fairly small foam pump, the FP 1.5-50, which actually is going to exceed these conditions. So usually a foam pump manufacturer from anywhere on the planet is going to pick this as a minimum and a minimum to size their foam pump. And that's the kind of data we're going to need to do a good job for you here at Fireline. And we're always pleased to review any calculations or design requirements you may have. And in closing, we appreciate it. Thank you very much.